Okay. Okay, so now it's notification. Okay, so welcome everybody into poster session 2. So thank you who joined earlier and were able to check all the systems. So hopefully for the rest of us it's going to work well. I know from my previous experience, previous sessions, we're likely going to have more people join in. So hopefully we're going to have a lively discussion here. So with that, we can start our presentations, and the first is going to be by Hoyan, right?
Right.
And so the title is going to be A Static Analyzer for Detecting Tensor Shape Errors in Deep Neural Network Training. So go ahead.
Okay. Do you see it?
Yep, we're good.
Yeah. Okay. I'll start. Hello.
Start.
Hello. I am Ho Young-Ju from Seoul National University. I present our static analyzer for detecting tensor shape errors from PyTorch deep learning training code. First of all, our static analyzer, which is called PyT, finds tensor mismatches from deep learning codes before the training. So what is a tensor shape error? Like a matrix multiplication, each tensor-related API in deep learning frameworks has several conditions about input tensors, dimensions, and shape. And those conditions are required to make the execution safe. To find these conditions, we should consider the potential shape of the external datasets and the semantics of the third-party libraries. So here is the overall structure of PyT Analyzer. First, PyTorch code and command line arguments are converted into PyTIR, which we defined. And next, PyT traverses the IR and collects the shape conditions of every potential execution path. From this page, the online checker simplifies the conditions and eagerly checks each trivially false conditions. Finally, Jet3's SMT solver tries to solve the collected constraint set and concludes that each execution path is valid, invalid, or unsolvable. In detail, we should define what is the constraint. In a word, constraint is a required conditions of the shape of the input tensors. If the constraint can be false in some paths, we should inform to the user that the path is potentially unsafe. However, it can occur path explosion in some complicated projects. To resolve this, we have set several assumptions and strategies such as path pruning and loop unrolling for constant bounded loops and handling special handling for the training loop. Through these steps, we can inform to the user what constraint can be violated and where the possible error is hidden in the code. In this image, this image is the result of the PyT command line code. So we have analyzed the official PyTorch examples from GitHub and compared with the former PyTorch analyzer of Hattori et al. From the benchmark, we can successfully analyze each project except two projects, which depends on huge third-party libraries which are not covered in the paper. Also, we have analyzed PyTorch questions in Stack Overflow, and we successfully analyzed our questions. And we analyzed several real-world projects, and we found an error in those projects, like this example. From this example, the code will crash only if the input image is a monochrome image, but it is hard to find that error in the path phases. We only have colored images in the test set. In conclusion, we have built a static analyzer which analyzes full training passes of the PyTorch training codes, and the performance is practical to integrate with IDEs as a real-time analyzer. PyT is publicly released at GitHub with a prototype VS Code extensions. Thank you for listening.
Thank you so much. So let's kind of send him applause so you can actually look at this reaction icons. You can send applause. Thank you. So if you have questions, you can ask. You can either ask right now or you can type it in our chat room and just use this kind of question tag to ask questions. It actually will kind of show a nice question and Hoyan able to type answer them. So anybody has questions? So basically my question, so so the PyTorch programs that you analyze, they're more dealing with images, right? It seems like.
Sorry?
So are those programs that you analyze mainly dealing with images, or what is it processing?
No, we analyze several projects like, sorry, I will see it.
Yeah.
Okay. There is many image processing, but there are also super or sequence processing and language models. So we can analyze PyTorch projects for all.
Okay. So we have a question in the chat. So how many false positives do you get?
There is not much false positives, but I have some false positive related with the value of the tensor itself, because we only consider the shape of the tensors, not the value of the tensors. But there is not much API related to the tensors, so there is not much.
Okay, well, thank you. So let's give another round of applause. Yay, you're done with the presentation. So the next one is going to be by Ajinkar Rajput. Can you start sharing your screen? So, and the presentation is Garuda heap aware symbolic execution. I think you're muted. Let's unmute yourself.
Am I audible?
Yep, now we can hear you. Yep. Go ahead.
Okay, so hi, I'm Ajinkya. I'm presenting, this is the ongoing research project at Indian Institute of Science in my lab. I'm a 6th year PhD student. So yeah, so, and this is the outline of the talk. The talk deals with symbolic execution. So I'll quickly in one slide summarize what symbolic execution is, and then why does memory modeling need special attention, then what's the current landscape, and then our approach and results. So a popular technique to reason about programs, and it's a systematic technique in which, so if you can see, there's a so if this is the program that you can see, usually what happens is it takes concrete inputs, and its internal state is also concrete, and finally a concrete output is generated. What happens with symbolic execution is the inputs to the program are symbolic. Therefore, your internal program state, which is the values assigned to variable, are expressions over those symbolic inputs, and your output is again expression over symbolic outputs, symbolic inputs. Therefore, we can reason about them by using a solver like Z3 or something, and therefore we can reason about program states and check for various properties of program. But there are a couple of limitations to this, and one of them is state space explosion, which is something that I'll skip in interest of time. And the other problem that we are solving is interaction with the environment. So whenever this program interacts with another, like let's say OS or the memory allocator or other libraries for which we don't have the code, it cannot calculate these functions f and g and h because it doesn't know what those instructions are executed are. Therefore, we directly jump to the case of handling malloc. And usually what symbolic execution engines do is they create abstract objects whenever they see a malloc with a base, which is the starting address, the size of the memory object created, and the contents are stored by different executors by different methods. So problem occurs when we are dealing with something like malloc of symbolic expression. So what happens here is you either have to concretize, because we don't know what this symbolic is. We whatever the symbolic expression, one value out of many possible evaluations, or we keep the symbolic expression that came in as the size variable as symbolic, and we deal with whatever side effect it creates, and we have to in our transfer functions we have to take care of those. So we trade off between this is basically when we choose either of these, there's a trade-off between coverage and symbolic size. So here's our idea. So what we saw is if we choose either of these, we when we concretize, we miss out on coverage, and when we consider the size or base as symbolic, which are basically the memory layout parameters which decide how the memory is laid out, we found out that if you consider everything symbolic, the abstract state is too generalized and the state space explodes really fast. So we do concretize, but we do it very smartly, and we do this by simulating memory allocator library. And in the symbolic state, we store the state of memory allocator library as well. So malloc allocator library has its internal data structures that limits the memory possible memory layouts, and thus limits the states that we have to check. It is still a incomplete state because we are still concretizing and we are theoretically not considering all the possible layouts. But yeah, it's a reasonable thing. So this is an example. Consider this sequence where you malloc two chunks of 10 bytes each and store it in x and y, and then free x, and then you encounter a symbolic malloc. So what happens is you can allocate either from here. If the symbolic malloc size is greater, then it can be allocated from here, which is x is free. So, and this is the free list, which basically makes this thing possible. And because of this layout, we know about this, what are the possible. So we proved the correctness of simulation in the results, and we found that these following CVs that we saw were detected by the Garuda, and these CVs were already known. These were not reported by Garuda. So I want to make that pretty clear that these are already known CVs, and we tested them as a sanity test of our technique. Our tool performed well on TestCom benchmarks, and further comparison and studies are going on. This is ongoing project, so we are trying to figure out more how better it performs. Any questions?
Oh, thank you so much for nice presentation. So let's give a round of applause. Yay. Yeah, so if you guys have questions, and you can unmute yourself and ask questions, or you can type in a chat. Okay, so I can start with the question. So do you there are any manual effort involved in the technique?
Yeah, there's a little bit of manual effort involved. So this technique is not memory allocator library agnostic. You will have to kind of create a simulator, and the gist of the memory allocator, the crux of the behavior of the memory allocator, you need it somehow. So you can either create a
so you need to model it.
Yeah, we need to model it. But we see that once you model it, it reduces solver queries and it speeds up the execution and reduces the state space as well.
Mm-hmm.
But I don't have those numbers right now.
Thank you.
That evaluation is going on.
Oh, it's fine. Yeah, it's fine. So what other questions you have? Anybody has? Okay. If no questions, we can move to our next presentation. So Yongyan, can you start sharing your screen? And do your recording?
I have a recorded video.
Yeah, so can you start sharing your screen?
Okay.
Jinkia, could you stop sharing your screen? Okay. You need to mute yourself.
Hi everyone, my name is Aoyang Yan. This is a presentation of our poster titled The Symptoms, Causes, and Repairs of Workarounds in Apache Issue Trackers. First, let me introduce the motivation of our work. In order to manage bug reports, issue tracker systems are widely used. Let's focus on Jira here. The typical resolutions of issues are fixed, invalid, duplicated, and won't fix. These resolutions have clear definitions. However, a less known resolution is workaround. Since the definition of workaround is vague, when most prior studies introduce the workflow of issue trackers, they don't mention workarounds at all. Many research questions on workarounds are still open. For example, what are the symptoms of these bugs? What is the trouble of directly resolving the problem? What are the repairs and impacts of workarounds? Our paper continues a prior empirical study to explore more on these questions. To construct the dataset, we collected 221 workarounds from 88 Apache projects. In our study, we manually inspected these workarounds. For a bug report, we read its title, description, comments, related issue reports, pull requests, and code changes to understand its symptoms, causes, and repairs. The categories of symptoms are predefined by prior studies, but the categories of causes and repairs are newly defined by ourselves, since no prior study has built such categories. We detected the bugs independently. For each inconsistency in our inspection results, we discussed on its bug report or even contacted their programmers by sending emails. Finally, we resolved all inconsistencies. This figure summarizes all of our empirical results. Our study answers these RQs. RQ1, what are the symptoms of these bugs? The answer is that most workarounds fix crashes and unexpected behaviors. RQ2, why are workarounds introduced? The answer is that the problems of more than half of workarounds are across projects or residing environments. About 1/3 workarounds fix problems on their own projects, but their repairs are imperfect, difficult to reproduce, modifications on non-source code, or solved by outside contributors. In a few cases, a bug report is marked as workaround because its problem is already fixed. RQ3, how do workarounds repair bugs? The answer is that there are various types of repairs, such as switching whole libraries, switching APIs, and modifying settings, build files and documents. Some workarounds have no repairs, since the problems are already fixed or cannot be fixed at present. RQ4, what are the associations among the symptoms, causes, and repairs of workarounds? The answer is that most associations between causes and repairs are straightforward. For example, if the operating system causes a bug, a typical workaround is to select alternative operating systems. Crashes are fixed as workarounds, often because they are fixed problems or they are problems residing in environments. Unexpected behaviors are fixed as workarounds, often because of flawed repairs and incompatible issues. RQ5. What is the definition of workaround? The answer is that 90.5% workarounds follow the conventional definition. Their problems are bypassed because their problems are impractical or difficult to be handled normally. The problems of 9.5% workarounds are already fixed in new versions or related issues when they are reported. The different definitions can be confusing. To solve the problem, we suggest that issue trackers can add other resolutions like fixed in other locations. That's the end of my presentation. Thank you for listening.
Okay, so let's give a round of applause. So we have a question. Am I echoing? Can you hear me echoing or not? So, so we have a question on the question chat. Maybe you can answer it, and we can start with the next presentation. Basically, just type in the chat. So our next presenter is going to be Aryaz. It's the first presentation, and the name is Crystal Blue, precisely and efficiently measuring the similarity of code. So go ahead, start. We cannot hear you. Can you unmute yourself? Yep.
Can you hear me now? Okay, good. Hello, everyone. My name is Aryaz Iqbali, and I'm from the software lab at University of Stuttgart. I want to talk to you about Crystal Blue, which is a metric for measuring code precisely and efficiently. So you have probably seen some models, mostly neural models of generating code, and more famous ones are the GitHub Copilot or the DeepMind's AlphaCode. And for evaluating how well these models perform, we need some metric for this evaluation. And one of the metrics that has been used a lot for tasks that there exists some ground truth as a reference is the BLEU score, which was initially introduced for natural language translations, but it's adopted in code evaluation as well. And there are some reasons and features of BLEU. One of them is that it's really fast to calculate. And it also works for partial code that is syntactically incomplete or doesn't compile or run. And also it's language agnostic. So any piece of code that can be tokenized can also be evaluated with BLEU. But there are some differences between programming languages and natural language. And I've shown one of these differences in these two examples. So these are two pieces of Java code that aren't related to each other in a semantic way. But as you can see, there are quite a few n-grams that are shared between these. And these shared n-grams cause a higher BLEU score than what the meaning of these programs are related. And these common n-grams are only here because of the syntax of the language or some coding conventions and so on. So we call the n-grams that appear because of these reasons and not the semantics, the trivially shared n-grams. And as you can see in this figure, and the ratio of shared engrams between two random pieces of text or code is much lower in natural languages like English or French than in programming languages like Python, Java, and C. And in more verbose programming languages like C and Java, this ratio is higher. So this is where Crystal Blue comes into play, and we do this in such a way that it's as fast as Blue, and it's even faster than metrics that are designed specifically for code like CodeBlue. It also works on partial code and also is language agnostic. And the way is that from a sample code corpus, we can extract these trivially shared engrams and then reduce or omit their effect during the calculation of the similarity metric, the Crystal Blue. And this metric allows us to better distinguish between the similar pairs of code and dissimilar pairs. And as you can see in this figure, Crystal Blue has a higher distinguishability, which is a new metric that we define, than Blue and also CodeBlue. Thank you very much for your attention, and I'm open to any questions.
So if you have questions, you can ask, unmute yourself, or you can type it in the chat under question label. Well, first of all, let's give a round of applause. Very nice presentation.
Thank you.
Okay. So I have a question. Do you think maybe because we know that everybody has their own programming style, you think it's going to make any difference?
Yeah, that's a very good question. Yeah, the programming styles are different, but they are less frequent than these general coding conventions or the general syntax of the language. So I think the Crystal Blue doesn't remove those. So probably code written by the same person would get a higher similarity than code from different people.
Okay, thank you. Other questions?
Hello, Arias. Thank you for the presentation. Will this tool be available as you mentioned in the last slide? And second question of mine is, do the scores change according to the formatting types or schemas that we are using, like mostly in scripting languages instead of Java like curly bracket languages?
Mm-hmm. So your first question, yes, it will be public soon. And for the second question, it depends on how the language is tokenized. So if like in Python, the tabs are tokens, then yes, they would be considered in the metric. So it all depends on how you tokenize the code.
Thank you.
So, yeah, and so what's next for your work?
I'm sorry?
What is next for this work? Or you're basically done with the tool?
Yes, it's almost done, and yeah, maybe more evaluation, but mostly showing how useful it is for different applications in code evaluation.
Anybody has other questions? Okay, well, let's thank again for
Thank you.
question. A nice presentation. And so we can now move to our fifth presentation by Alessio. Did I say it correctly?
Yeah, correctly. So let me.
So you're going to present Krishy. Okay, towards generating test case from accident sketches. Go ahead, start sharing your screen.
Let me start sharing. Hope you can see my slides.
Yep.
You see the slides or the one with the notes?
There is no notes.
Okay, then I'm sharing the right screen.
Yeah, we
So
can
welcome,
hear you and
everybody.
we can see slides. So go ahead.
Okay, great. Welcome, everybody. My name is Alessio Gambi, and this is a joint work with University of Passau and EMC, University of Applied Science, Krems in Austria. I developed this tool in collaboration with students like Wang and Jazim and Professor Fraser that you may know for other works. So the goal of this work, of my research, is to test self-driving cars and advanced driving systems. And the reason why is that if you don't test them, as usual, bad things happen, people dies, and we want to avoid that. Now, how those systems are usually tested is by driving those cars around, the so-called natural field operational test. It has been proved that to ensure that vehicles and software driving them are safe, it would require billions of driving miles. So those technique for testing self-driving cars have been coupled with something different based on scenarios and simulations. So the idea is that we can create inside physical simulators like BeamNG.Tech, which is the one that I use for this work, different scenarios. So we can create very specific situations and test the software in many different conditions. Now, the challenge here is how do we select them? Because when you can simulate everything, then becomes an issue to choose what to do. This is a classical testing problems, right? This input space simply is too big. So in this work, we make the observation, or we argue that relevant scenarios are the ones that involve that are safety critical. And one straightforward way of identifying them is to relate to crash accidents. So there is a critical situation, a crash that happened. And the nice thing is that police tends to, or in general, those crashes are documented. So you have a very large number of different critical situations that you can refer to while testing your cars. Now, the challenges of this, and this is an example of an actual crash from the National Highway Traffic Safety Administration, NHTSA, for this SIREN study, is that text and images, that's how they are documented, those crashes, must be analyzed and interpreted. Okay, those are the challenges that Krish try to address. So specifically, Krish look at the sketches, and Krish stands for critical scenarios. And what it does is it takes the picture, the sketch. We do a slightly manual processing to simplify subsequent operation. And what it does, it uses image analysis to extract information about the roads, geometry, and whatever net possible lane markings and lane configurations. Then it tries to identify vehicles in those sketches by means of what we call oriented bounding boxes. So it tries to identify where the vehicle is and its rotation angle. Now, from this, we interpret the position and of those, the relative position of those boxes to derive a trajectory of the cars, and then we interpolate them using, for example, Bezier interpolation. At this point, we extracted enough information from the images to configure a simulation and run it. So the idea is that now you have a running simulation, and then you can use this simulation to derive test cases for your self-driving car. In this work, we investigated the generation of the so-called abstract scenarios that are suitable for testing trajectory planners and actual three-dimensional driving simulations. So here I report a little video. So on top, you see the input of our tool, the sketch, and below you see two of the outputs of our tool that are automatically generated once we pre-process the image. So I'm gonna play them, and you see that the simulations that we generate try to capture the main elements of the road and the trajectory of the cars. So we implemented this tool and we started evaluating our approach with it. And so far we managed to take 50 randomly sampled sketches like the one that I show you, involving not just curve crash roads, but also intersections and the like, from the SIREN database. SIREN is a study from NHTSA that focuses especially on critical situations like crashes. Then we manage always to create simulations that result in an impact, though most of them are actually perfectly matching the input, meaning that the parts that are damaged from the car are indeed the same that are going to be damaged during the simulations. And a nice thing is that it's very efficient. So image processing is not time consuming in this specific context. So in the less of a second, we can generate one of these simulations. So for the future, the idea is that we have a previous work that solves a similar problem using natural language processing, so parsing the description of the crash to generate the simulation that was published at FSC. And we want to combine image analysis and natural language processing together to improve our scenarios. Besides this, our next step would be to generate actual test cases from the scenarios, because they lack, for example, test oracles, and also try to increase the criticality when necessary using search-based algorithm. So this is all of it. Here you have my contact and a summary, and I'm ready to take your questions if you have any.
Thank you so much. Here's all applause for you. Very nice presentation. So,
yeah, I have a question.
okay.
And first, thank you very much for the nice talk, and it's a really interesting topic. First of all, I have a question about how much data do you have? You mentioned that you tested 50, but do you have more data?
Yeah, so we have data, we have as many reports as published by NHTSA. And so far, those are publicly available. They are anonymized because they cannot report the name of people, but we are about, I don't know, 10,000 in different databases. So each database has a slightly different visual format. We focus only on this siren. And yeah, the good thing for us, but the bad thing for the society is that this database's size keep increasing. You know, so we want to, so this is good for studying, but bad, of course. But yeah, there is enough.
Yeah, and one more question. How do you determine the speed?
Okay, this is a very good question. So in our first implementation, we assumed that the vehicle start from standing position. So if you see it from the video there, and then we compute a constant speed. So they will accelerate up to some target speed, and then they will keep the speed. What we are working on now is to extract also the speed limit. So if you look at the very first, it's small, but if you look at here in this picture here, it says speed limit 55. So that's what we are doing now, try to extract additional information, and then when the speed limit is fixed, then we try at least to take the cars at that speed. However, if you look, we didn't have time, but if you look in the description, there is no specific speed limit described here, so we have to guess. That's why we plan to use search algorithm that, given a reference trajectory, can play around with some parameters, speed and other things to increase or decrease the criticality of the resulting crash.
Thank you.
For the question.
Anybody else has questions?
Yes, thank you. Very good presentation. I like it. And just one concerning the pre-processing you have to do. What are the actual steps that you have to perform there? I think of scalability. Isn't that a problem there?
Yeah, nice. You nailed one of the issues. So the pre-processing that we do is, so we are software engineers, so we are not super expert in image processing. So given this picture, the processes consist in taking out those squared elements, so those rectangles, and basically link the little lines that define the roads. So this is basically what we need to do for having this sketch only, road only sketch. For the other one, it's mostly getting rid of text and these other elements that we cannot yet processed. Actually, now we can process node directions and speed limit as well in the next, but it's not in the paper yet. So that's basically is cleaning up a bit the mess.
Okay, thank you.
Anybody else has other question? So can it actually handle multi cars or just right now 2 cars? Or it doesn't matter?
Sorry?
Can it handle like multi-car collisions too?
Not yet. It's part of our future work. That those reports from NHTSA always identify 2 main actors that are involved. So, and that's why they are colored. There are sketches where it shows other traffic participants that were there but did not take part of the action, and they are in white. But the approach is can be extended. Of course, the more cars you add, the more complex it is to generate a simulation that makes everybody move at the right way. But yeah, that's part of the future work.
Okay, well, thank you so much. Let's give Alessio a round of applause.
Thanks for your
question. So with that, yeah, great work. So and now we're going to move to our last presentation by Moo-Soo Kim, and it's named Deep Learning Based Production and Test Bugs Report Classification Using Source Files.
Okay, I will play my presentation video, my screen sharing.
Go ahead.
Okay. Hello, I am Moo-Soo Kim. I will present our research paper titled Deep Learning-Based Production and Test Bug Report Classification Using Source Files. Information Retrieval-Based Bug Localization, named IRBL, is a technique to automate the bug localization task. There are 2 types of bugs, such as production and test bugs. The production bugs are located in the production source files, and the test bugs are found in the test source files. If a bug report describes a production bug, a developer can choose only the production source files as the search space because production bugs are known to exist only in production files. Similarly, a developer may set only test source files as the search space for test bug localization. In our previous study, we found that classifying these bug types and such stable search space selection improves IRBL performance. Although classifying the bug reports can improve the IRBL, manually reading, understanding, and classifying bug reports is time-consuming. Therefore, an automatic classification method is needed. Deep learning is a feasible and popular solution for automatically classifying documents. However, there are 2 problems when applying deep learning for the bug report classification. The first problem is the insufficient bug reports. The number of bug reports for each software project did not exceed 1,000 in our experimental dataset. In the worst case, the total number was less than 100. Especially, the number of test bug reports was less than 100. This problem can lead to the overfitting problem of the classification model. The second problem is the sparse bug reports. Each bug report could be unique because the bugs described in the reports are different. For example, deep learning cannot learn about a production function name, such as list custom resource by labels, because this report was the only bug report in this project having this keyword. To solve these problems, we propose to use the source files to train the automatic bug report classification. Source files can be divided into production and test-related items. The number of source files is greater than the number of bug reports, and especially the number of test files is significantly larger than the number of the test bug reports. In addition, the source files contained considerable textual information about the software. Therefore, source files are sufficient and less sparse dataset than bug reports to extract production and test-related textual features. This figure is an overview of our proposed method. Our deep learning model is an extended version of TextCNN for entering multiple input features. First, we train the source model by source files based on this deep learning model. Our method divides the source files into the file name and content, and enters these two inputs into the multiple input layers and embedding layers. We apply fine-tuning-based transfer learning to train the bug report classifier from the source file classifier. We initialize the target model's parameters for the bug report classifier using the source model trained with the source files. Then the bug summary and contents are entered into the source model for training the final classifier. After the tuning, the classifier can predict the bug type from the new bug reports. We manually classified the bug reports and then selected 4,059 bug reports for our experiment. For the classification evaluation, we used the F1 score for each type. We compared our method with bug report training and source file-based training. And each method has two variations depending on the input feature and the number of the input layers. We confirmed that our final proposed method is superior to all comparison targets. We confirmed that the source files is crucial dataset that can be used effectively for bug report classification by conducting experiments. In the future, we plan to these three works for advancing our method. Thank you for listening.
Hi, thank you for the presentation.
Okay.
Working hard recording it.
Mm.
So, what questions people have?
Hello, Miso. Thank you for the presentation. I actually wonder the extendability of this solution to maybe all kinds of bug reports, because each bug report schema may have different settings. For instance, in Jira, we can customize the bug report fields. Of course, we have a common text section, but there are some customizable label section of Jira, or in GitHub issues. We don't have any structured labels, but we can only add tags with custom texts indeed. So do your solution, or can we scale your solution to our custom issue tracking schemas?
Okay. So I agreed with your issues you mentioned. So, and now we don't have any exact solution and schema for solving this issue, but we plan to study with many bug reports and many tracking systems for improving the scalability of our method.
Thank you, Anat.
Okay, thank you.
Anybody else questions? I don't have questions. It's like almost 2 in the morning at my time, so my brain is like, let's hear all the time. So, well, if nobody has any questions to Misu, we can, give another round of applause. And I think that's it. We are done with our poster session. So thank you so much hanging around here, asking each other questions. I appreciate it. So I think there are some 10 minutes left until the end of the 1 hour session, and maybe you could go and look around for other rooms, see what's going on there. Well, thank you so much, guys. If you're going to come to ICSI, then I will see you there.
Yeah,
Bye.
unfortunately, I
Thank
cannot,
you.
but I would have loved to.
Next time.
Yeah, next time. Bye. Thanks. Ciao,
Bye.
ciao.
Thank you, everyone.
Bye, everyone. Thanks.
Bye. Thank you.
Organizing.